Now this knob interface is quite satisfying to play around with, but not yet perfect. Because the truth is, this is only a mock-up, inspired by the open source project SmartKnob, whose first video hit YouTube almost 2 years ago. Now back then I was fascinated how satisfying to use this demo looked, and thus I immediately checked out the schematic of the project. And to my delight, I was familiar with almost all hardware used there. Except of course one, and that was the magnetic encoder, that I of course also had to use here for my mock-up demo. And yes, such a magnetic encoder is similar to such a rotary encoder, which I already used in tons of previous projects before. However, there are some rather big differences, which can not only transform any motor into an awesome input device, but also makes it possible to convert, for example, a powerful BLDC motor into a kind of stepper motor. So in this video, I will tell you all about these so-called motor encoders and why you should definitely consider using them in your next projects. Let's get started! This video is sponsored by Solo Motor Controllers, who sent me one of their motor controller boards for this video. And I gotta say, not only the hardware quality is amazing, but also the software side. Meaning that after hooking up my motor with Encoder, about which I will talk about later, it all in all took me maybe around 15 minutes to get it all up and running, with amazing precision. And best of, the controller also functions with minimal external components and even comes with Arduino and Raspberry Pi support. If that sounds interesting to you, then click the link below to check out their products and YouTube channel. Now first off, I think it is best to take apart such a common rotary encoder to get a basic idea of what is going on. Inside we can find a round pad with an interesting metal pattern on it that is of course conductive, while the black stuff is non-conductive. And on the other side we got two metal pins that sweep across this round pad, and in this encoder example they are called clock and data, but oftentimes they're simply called pin A and B. And what happens is that as soon as you apply power to this thing and start spinning, for example clockwise, one of the pins will firstly touch the metal, complete the circuit, and thus get pulled down low to ground, before the other pin does the exact same thing. Afterwards, these connections get interrupted, and the pins get once again pulled up to the supply voltage. This process repeats for every metal jack on this pad, meaning that at the end we get a voltage signal like this on the oscilloscope. Here every voltage pulse not only tells us that movement took place, but by looking at which signal A or B came first, we can also tell in what direction the encoder got turned. You see, for the clockwise direction we tried out, it is B before A, but when we turn counterclockwise, it becomes A before B. This has to do with the layout of this pattern, and it is maybe not that easy to grasp with such a purely mechanical encoder. But if we for example compare it to an optical encoder that also uses a similar pattern through which light shines through, then we can easily see that one light sensor detects light and thus triggers before the other one. And thus, depending in which direction we rotate, we once again get these different voltage signals. And that is basically always the main functional principle of every encoder. The only addition you sometimes see is a third pin labeled X, which stands for index. And this one creates a voltage pulse when one complete rotation of the encoder is done. So with this knowledge in mind, we could mechanically connect this encoder to a motor shaft and turn it, in order to find out in what direction it spins and what position the shaft takes. But there are two problems here, with the first one being that not every motor comes with a shaft on the front and back, I mean, the one I want to use for my smart knob mockup comes with no shaft sticking out. And the second problem is the resolution of this encoder, which completes one rotation in 20 increments. That equals a resolution of 360 degrees divided by 20, so 18 degrees per step. That means we would have to turn our motor quite often to get anywhere on the LCD user interface. And of course, when it comes to positioning tasks later on, then 18 degrees is really imprecise. But don't worry, because there are dozens of encoders available out there. And one of the most popular ones seem to be this board, based around the AS5600IC, which, according to its datasheet, is a magnetic rotary position sensor. What it can do is determining the position of a magnet on top of it, which therefore needs to have its north and south pole on one side. And that is normally not the case with more generic magnets. But thankfully the board came with such a magnet, and thus by securing it onto the motor shaft so that the magnet can perfectly rotate, hooking up wires to the board, securing it on top of the magnet with bolts, and hooking everything up to a microcontroller, it was time for some testing. Now I'm using some I2C example code here to spit out the raw angle values through the serial monitor. And as you can see, this setup seems to work perfectly fine. This time we got a resolution of 12 bits, aka 4096 steps, which in theory equals 0.088 degrees per step, which is a huge difference to before. The only problem with such magnetic encoders though is that good positioning of the magnet on top of the 4 integrated Hall effect sensors is crucial. And sometimes you can have problems if there are stray electromagnetic fields around you. But that is not really a problem when it comes to using such a motor with encoder as an input for an awesome mockup project, which I might improve in the future, not sure yet. But for now, let's close this chapter and move on to other motors to which we would like to add encoders to precisely control their position. And I know what you're thinking, don't we already have stepper motors if we want precise positioning? And yes, by hooking them up to dedicated stepper motor drivers, it is super simple to let them go in one specific way and then another and then another and so on. I mean, that is the reason why they're being used in, for example, almost every 3D printer. And if you want to know more about them, then definitely check out my previous basics video about them. But anyway, stepper motors are not always the best choice. For example, when building a small robot, it makes more sense to use cheap and small DC motors. Here you can see though that even when using two identical ones, the robot will still lean towards one side when going straight, because no two motors are exactly the same. In such a case, adding encoders and controlling the motors in correlation to those could easily solve this problem. Or let's say you want to do positioning like a stepper motor, but with a more powerful and fast BLDC motor. Once again, adding an encoder could do just that. And luckily for me, I got this AMT 1021 lane around, which apparently uses some kind of capacitive technology. So I'm not entirely sure how exactly it works, but after attaching this encoder to my dual shaft motor and having a look at the A and B pin on the oscilloscope, it seems to spit out the voltage signal we are all familiar with, and this time with a resolution of 2048, aka 0.176 degrees per step. Very nice. So to get this motor encoder setup completely functional, I firstly added a 3D printed enclosure to it all, and then unpacked my Solo Uno motor driver. Such a driver, by the way, is mandatory because BLDC motors are not really easy to control, like for example a DC motor. And since this one can handle up to 58 volts and 100 amps, and comes with an encoder input, it should work just fine with my motor setup. All I had to do was hooking up the encoder and motor wires like the user manual describes it, connect power and hook it all up to my computer. With the given motion terminal software, the motor then got identified, the encoder tested, and all I pretty much had to do was fine adjusting the P and I values for the PID control. At the end, I could then select a torque or speed mode, for which the encoder is already useful to obviously measure the exact speed of the motor. But then we of course also got the positioning mode, where I can simply select a desired position and the motor moves there fast and powerful. Of course, we can fine adjust lots of settings here to go, for example, slower, with less power and much more. And overall, it is awesome to see that such precise positioning tasks are this way pretty easy to do with every motor type out there. With that being said, you should now be familiar with motor encoders and maybe got inspired to use them in your next projects. If so, consider supporting this show on Patreon to keep it going. Don't forget to like, share, subscribe and hit the notification bell. Stay creative, and I will see you next time.